Okay, this video is going to illustrate some ways that you can use molecular orbital diagrams to make some predictions about certain small molecules. So this is just another way of looking at how molecules might form, and consider that the bonding of the atoms, instead of looking just at their atomic orbitals, so that's what I have down each side, they get mixed and create a new set of molecular orbitals. So your book gives you two possibilities. If you're working with atoms that are smaller, nitrogen or smaller, you would use a diagram like this. And if you're working with atoms that are larger than nitrogen, the bonding will look a little bit different. And we're starting at the 2s and the 2p's because those are the valence electrons that we would be considering in the molecules. So I just basically made these, and then I just photocopied several examples to use. So what if we were trying to look at a molecule of C2 compared to C2 plus, and the question is which one is more stable? So the way you would use the molecular orbital diagram is one is carbon and the other is carbon. And to figure out which one is more stable, we would need to know the bonding present. So carbons are 2s2, 2p2. So there are 4 valence electrons in each carbon, and then those will populate the molecular orbital. So 4 electrons will populate here, which basically those are going to cancel each other out, and 4 electrons will populate here. 1, 2, 3, 4. And so what we might be asked is, what's the bond order for C2? So we take the bonding electrons, 2, 4, 6, and subtract the anti-bonding orbitals, divide by 2, and the C2 molecule would have a bond order of 2, which would mean a double bond would exist between those. The molecule would look like this. And then the other question was, well, what about C2 with a positive charge? The way that would look is exactly like this, except if it has a positive charge, that means it has lost an electron. So if you remember, this was the last electron that we placed, so let's imagine that it's not there. The molecular orbital diagram for C2 plus looks like this. And basically it's only different by the fact that it has 5 bonding electrons instead of 6. So the bond order is, 3 divided by 2 is 1.5, which means it's a weaker bond and would therefore be less stable. So we can use molecular orbital diagrams to make conclusions about which one is more stable. The one with the higher bond order is going to be the more stable one. Another question that you might be asked is, well, just does a particular molecule exist? Is it likely to exist? In this case, we're looking at the potential of a molecule between boron and carbon. Is that likely to exist? And so we can do the same thing. Boron is 2s2, 2p1. So this is my boron side, and this is carbon. 2s2, 2p2. And then we fill them in accordingly. 4 electrons will go here, 1, 2, 3, 4, and then 3 electrons here, 1, 2, 3. And so again, we can see that the bond order is going to be 5 minus 2 divided by 2. 5 bonding electrons, 2 anti-bonding, so the bond order is going to be 1.5. So we might think that, yeah, this molecule could potentially exist. All right, now I'm using the other molecular diagram because I'm looking at the potential for O2 minus to exist. What kind of bond order does it have? And maybe other questions might be, is it paramagnetic or diamagnetic? All right, so we're going to bond oxygen to oxygen. Oxygen is 2s2, 2p4. So it has a total of 6 valence electrons. The other one is the same. But we're considering a particle of O2 minus, which means it's gaining an electron. So once I get done filling into my molecular orbitals, I'm going to actually add an additional electron. So these 4 electrons get filled here. 1, 2, 3, 4, and we just fill them in from the bottom up. Now I'm going to put 8 electrons into these orbitals, and they go in this way. 2, 3, 4, 5, 6, 7, 8. This would be the correct orbital diagram for O2. I'm going to add an additional electron because I'm looking at O2 minus. And it goes here. So when you have pairs of orbitals that are the same energy, you do one at a time before you double up. All right, so I should have 9 electrons here. 2, 4, 6, 8, 9. The question of is it paramagnetic or diamagnetic, that's a property that we looked at earlier in the semester. If all the electrons are paired, it's diamagnetic. If some of them are unpaired, paramagnetic. So right here, this makes it paramagnetic with 1 lone electron. Another question could be, what's the bond order? Again, we can count bonding electrons, 2, 4, 6, 8. Subtract the anti-bonding electrons, 2, 4, 5. And again, we have a bond order of 1.5. Now, one thing that's interesting to notice is, how does the O2 molecule compare? If I hadn't added that extra electron in right here, I would have had 8 bonding electrons, but only 4 non-bonding. And so actually what that means is O2 has a bond order of 2, O2 minus has a bond order of 1.5. This is the more stable particle than this one. Those are just some conclusions that you can draw by using the molecular orbital diagram. One last one. Would neon exist in the diatomic phase? This is another thing that, just whether something would exist or not. Neon is 2s2, 2p6. So all these are filled. Likewise, another neon. So a total of 8 valence electrons for each one, and then we're going to dump them into these molecular orbitals. 4 electrons, and I've got 6 here and 6 here, so I'm going to fill up from the bottom 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so obviously if these are all filled, then these are all going to be filled. So what's interesting to note then is if I look at the bond order calculation, I have 2, 4, 6, 8 bonding electrons and 2, 4, 6, 8 anti-bonding orbitals. So the bond order is 0. That tells me that I should not expect neon to exist in the diatomic phase, and in fact it doesn't. It only exists as regular single molecular neons.